Hi everybody, welcome to another video in course Algebra, section 3.5, rational functions and their graphs. Rational function. A rational function is a ratio of two polynomials. So we have p of x and q of x are polynomials, and we divide them. Since we divide them, the denominator cannot be equal to 0, otherwise it will be undefined. So once again, a rational function is a ratio of two polynomials where denominator not equal to 0. And the domain of rational function is all real number excluding the real 0 of q of x, meaning that the bottom cannot be equal to 0. Right. Now let's look at this example. Find the domains of the following function. So we have a rational function. So the denominator cannot be equal to 0. So we just let the bottom not equal to 0. In that case, we have x minus 2 not equal to 0, plus 2 on both sides, x not equal to 2. Right, so we can draw the graph for the solution. It can be anything except for 2. So can be anything on the left and on the right of 2. So in interval notation, we will write negative infinity to 2, then 2 to infinity, and then there's a union of those two intervals. Right. So everything but 2. Similarly, for this rational function, just let the denominator not equal to 0 or the bottom not equal to 0. So we have x squared plus 4x minus 3 not equal to 0. And now we just solve for x. Here I will factor to get to negative 3. So actually I think there's a typo here. I turn that to a plus. Right. So we have x plus 3, x plus 1 not equal to 0. Right. So here we say x plus 3 not equal to 0, x plus 1 not equal to 1. Here should be n. So x plus 3 not equal to 0, x plus 1 not equal to 0. Subtract 3 on both sides and subtract 1 on both sides. So x not equal to negative 3, x not equal to negative 1. Right? So on the number line, negative 3 and negative 1 can be anything but that. So cannot be negative 1, cannot be negative 3. Or in interval notation, we write negative infinity to negative 3 parentheses union negative 3 to negative 1 union negative 1 to infinity. Next, we have this example. Once again, to find the domain, the denominator on the bottom not equal to 0. So we have x squared plus 1 not equal to 0. Right. Of course, we just solve it. We'll not use factoring here. Just subtract 1 on both sides. So have x squared not equal to negative 1. And then we can take square root on both sides. And then when we do that, there's a plus or minus. And negative 1, square root of negative 1, we have x not equal to plus or minus I. Since the domain is all real numbers, excluding the 0, and so here we have x not equal to imaginary, meaning all the real numbers will work because all the real numbers not equal to imaginary. So we say all real numbers are acceptable. Meaning that it will be the whole number line. And we will write negative infinity to infinity for real numbers. So once again, domain of rational function, just set the denominator not equal to 0. Right. Next, the asymptotes notation. When x go to c, the superscript plus, meaning that we're approaching to c from the right. The superscript minus, it is from the left, but not equal to. So it's getting closer and closer as we want to, but we'll not get there as close as we want to. Right, x go to infinity. We do not need the superscript or negative superscript for positive or negative, because when we go to infinity, it is always go from this side to infinity. We cannot go from the right side of infinity. Likewise, when we go to negative infinity, we have to go from this side. We cannot go from the left of negative infinity. And we use that notation to define the asymptote. So pretty much x go to a number from the left or from the right, or x go to infinity. Definition. Vertical asymptotes. What is vertical asymptote? Could be in plural potentially. The line x equal to c is a vertical asymptote of the graph of f of x. If f of x go to infinity as x go to c, could be from the left or on the right. Right. So the vertical asymptote, the vertical line, we have x equal to a constant, c is a constant. So here we have the graph, and this is the vertical asymptote. And his value is c. So the vertical asymptote is the vertical line where when the function gets close to it, let me just make it clear. So the values of the function as x gets close to c from the left side or on the right side, the values of the function get to go to infinity or negative infinity. So here, if we use the notation, for example, from this one, we said x go to c from the right hand side, and the function go to negative infinity. For that graph, x go to c from the right side, the function go to negative infinity. And here we have x go to c from the left side, and the function go to infinity. So if we use that notation, we can write for that particular example. The bottom line is the vertical asymptote is the line where the function approaching to, and there might be more than one vertical asymptote. Horizontal asymptote, there's only one. For this type, the way we define rational function, there can only be one rational, one vertical. The way we define our rational function, there is only one horizontal asymptote, or maybe none. Right. So the horizontal line is y equal to something, a constant, when the function approaching to that constant at x go to infinity or negative infinity. So we have a horizontal asymptote. And the function we're approaching to, by the way, this is d, and the function approaching to d from the left side or from the right side. By the left side or the right side here, I mean, is from the smaller values of c and the bigger values of c. So here we have the bigger values of d, and we say as x goes to negative infinity on this one, the function go to d on the plus side, because whatever the values here is going to be bigger than d, the values of the function bigger than d, but getting closer and closer to d, so that d to the plus side, the bigger side. And here when x go to infinity, the function go to d from the smaller side. By the way, like I said, this is just for this particular example. We might have the graph going like this, and so we have different scenarios here. And finally, if it is not horizontal or vertical, we call the slant asymptote or the oblique asymptote. We just have the equation of the line, and pretty much this is where the function approaching to. And notice that I brought in the dashed line, the asymptote is not part of the graph, right? So the function approaching to it as x goes to infinity or negative infinity. Right, now a few more things to consider. Vertical asymptote, there may be more than one vertical asymptote. Horizontal asymptote, there can be one or maybe none. Slant asymptote can be one or none. But the distinction for the vertical asymptote is that the vertical asymptote, when x goes to a number c, the function is undefined. So there's a break in the function for the vertical asymptote. So notice that for the vertical asymptote here, the bottom is not equal to, is equal to bottom equal to 0, so the function is undefined, and this is the gap in the function, bottom equal to 0 for the vertical asymptote at x equal to c, so the function is undefined. Yeah, this is only for the vertical asymptote, so f of x is undefined. At x equal to c. So for vertical asymptote, where's the gap in the function where the bottom equal to 0? Right. Now, go to finding the asymptote, finding the vertical asymptote. Let f of x be a rational function, then y equal to c. This is the vertical asymptote, sorry. Then x equal to c is a vertical asymptote if at x equal to c, the bottom equal to 0. So to make it undefined, but we need the top not equal to 0. Because when both of them equal to 0, there's a hole in the graph. We will talk about that. But what we need is the bottom equal to 0 and the top is not equal to 0. When both of them equal to 0, there is a hole in the graph. We'll see that in a minute. Right. And the horizontal asymptote, I'll just go quickly and then we go back to this later. For horizontal asymptote, we will use degree of the top and the bottom. Now, if degree on the top is less than the bottom, then the bottom goes to infinity faster than the top. Right. Just give one example. In this case, on the first case here, if degree at the bottom bigger, meaning it go to infinity faster than the top. So we have something and then the bottom go to infinity very fast. When we divide by the very big number or very small number, when the bottom goes to infinity, then this will go to 0. If the bottom as x goes to plus or minus infinity, because when x go to infinity, the bottom will go to infinity faster than the top, because it has the higher degree than the top, so it go to infinity faster. And since we divide by the bigger and bigger number, we get smaller and smaller quotient, essentially go to 0. Right? And when degree are equal, we just divide the leading coefficient, and when degree on the top bigger, so we're talking about something like this. As x go to infinity, x go to infinity, the top will go to infinity faster than the bottom. So in this case, it go to infinity. So that's why there's no horizontal asymptote. A way to memorize this is, I found this on the internet. And it doesn't mean anything, but this is a abbreviation. Bigger on the bottom equal to 0. I mean y equal to 0. Bigger on the top, there is none. If the exponents, the power of x, are the same, exponent are the same, divide the leading coefficient. Right. So let's say it. If we have x squared plus 5 over 2x squared minus 1, when the exponent are the same, x squared and x squared, just divide the leading coefficient. So in this case, we have 1/2. So once again, bigger on the bottom, y equal to 0. Bigger on the top, there's none. Exponents are the same, divide the leading coefficient. In this case, we have 1/2. Right. For the slant asymptote, to find it, we require to have two conditions. That's why I write the checkbox here. We have to have both of this. When the degree on top is 1 more than the bottom, and when the remainder is not equal to 0 when we divide the rational function, divide the polynomial in rational function. In that case, y equal to the quotient is the slant asymptote. Here we have some example. Find the vertical asymptotes. For the vertical asymptote, we need the function to be undefined, so the bottom must be equal to 0. But we don't want the top to be equal to 0, because in that case we will not have the vertical asymptote, we have a hole instead. You will see in this first example. Right, so once again we need the bottom equal to 0, so the function is undefined, and then make sure that the top is not equal to 0. Right, so for the bottom equal to 0, we have x squared minus 3x plus 2 equal to 0. So we will factor, right, multiply to 2 and add to negative 3, so it have to be minus 2 and minus 1. So in that case, x squared minus 3x plus 2. So we have x minus 2 equal to 0, x minus 1 equal to 0, and then plus 2 on both sides, plus 1 on both sides. So if x equal to 2 and x equal to 1. Right. Now, that will make the bottom equal to 0. That will make the function undefined. Now we just need to make sure that the top is not equal to 0. We do not need to solve for the top. We just say when x equal to 2, the top equal to 2 squared minus 1, it is 3. And that is not equal to 0. So it is good. We have x equal to 2 is a vertical asymptote. And now we test for x equal to 1. The top in that case will be equal to 1. Substitute for x. And that equal to 0. It is equal to 0. So this fail. X equal to 1 is not the vertical asymptote. So we said x equal to 2 is a vertical asymptote. Right. Now let's just graph and see if it is the vertical asymptote. X squared minus 1 divided by x squared minus 3x plus 4. That's it graph. Wait. Plus 2. Right, with that, you see there's a vertical asymptote here at x equal to 2. At x equal to 1, there's nothing special there. We won't be able to see that on the graph. But if we have to sketch the graph again, this is just a sketch. So we have the graph kind of like this. Just a sketch, it's not very good. So we have the vertical asymptote at x equal to 2. But when x equal to 1, there's a hole in the graph. The calculator do not show that, does not show it, but we see that there's a hole because the function is undefined, but it's not a vertical asymptote. So we just skip one point, and in that case we only find vertical asymptote, so we do not find a hole. But if we write that, we can say f of x, the graph of f of x has a hole at x equal to 1. Right, so Very straightforward. We'll just let the bottom equal to 0 and then make sure that the top is not. So here we let the bottom equal to 0 and we make sure that the top is not. So x squared minus 4 equal to 0 and then the top is not equal to 0. So x squared minus 4 equal to 0. In this case we do not need factor. I'll just do using the square root properties. So if x squared equal to 4 and take the square root on both sides. So if x equal to plus or minus square root of 4, we have plus or minus 2. At x equal to 2, I'm going to put 2 in the top. We have 1, and that is not equal to 0. So that's good. This is a vertical asymptote. When x equal to negative 2, the top equal to negative 2 in for x. And that is negative 3, and that is not equal to 0, which is also good. So we have another vertical asymptote. So we have two vertical asymptotes in this case, x equal to 2 and x equal to negative 2. Let's look at the graph. If we want to enter the function as a rational function, hit alpha y equal, and then we have x minus 1 on top, x squared minus 4, then we graph. You see there's a vertical asymptote at negative 2 and at 2. Right. Now go to the next one. Once again, we need the bottom equal to 0 and the top is not. So x squared plus 1 equal to 0. Here we just subtract 1 on both sides. We did one similar like this earlier, and take the square root on both sides. Right. This is not a real number. So in this case, the bottom will never be equal to 0. So in this case, there's no vertical asymptote, because the bottom for all the real number values for x, it cannot equal to 0 because we have imaginary here. So for real numbers, the bottom not equal to 0, because for all real number for x, the bottom cannot equal to 0. So in this case, if we look at the graph, x squared plus 3x plus 5, x squared plus 1, we see we will not have the vertical asymptote in this case. Right. Now, for horizontal asymptote, we will base on the degrees of the top and bottom. So in this case, for the first example, let's write down the mnemonic we have earlier. Bigger on the bottom, y equal to 0. Bigger on the top, there's none. Exponential are the same. Divide coefficient. Right, so that's what we use for horizontal asymptote. Right, now we look at the degree on the top. The highest power of x on the top is 2. Degree at the bottom is also 2. So in this case they are equal. So when exponential are the same, we divide the coefficient. So the coefficient pretty much coefficient of x squared at the top and x squared at the bottom. So equal to 2. So we have y equal to 2 is the horizontal asymptote. Right. Let's see the graph. For x squared plus 3x to x squared minus 3. The graph gives us, right, you see the x y equal to 2 is the horizontal asymptote. The graph will get closer and closer to it. Right. Next example, we have degree on the top, power of x on the top. The highest power of x on the top is 1, and degree at the bottom is 3. The power of x is 3. So in this case, degree on top is less than degree at the bottom. Or say degree at the bottom is bigger than degree on top. So bigger on the bottom, y equal to 0. Is the horizontal asymptote. Very straightforward, the scenarios. Here we have degree on top. Is equal to 3. Degree at the bottom is 2. Now degree on top is bigger than degree at the bottom. So bigger on the bottom, there's none. So there's no horizontal asymptote. Right, very straightforward, those scenarios. Right, for the slant asymptote, just go back and review. For the slant asymptote, we need two things. The degree on top is 1 more than the bottom, and the remainder not equal to 0 when we divide them. So first, this degree on top 1 more than the bottom. Now degree on top is 2, degree at the bottom is 1. Yes, degree on top is 1 more than the bottom. So when that is the case, we just go ahead and divide them. So in this case, since we divide by the binomial degree 1, here we can just use synthetic division. remember when we divide by x by 3, actually the number is going to be 3 on that corner. Right, x squared minus 4x and 7. Right, drop the 1 times 3 is 3, negative 4 plus 3 is negative 1, 3 times negative 1 is negative 3, and then that gives us 4 as a remainder. Right, so this is not equal to 0, so there are two criteria. Degree on top is 1 more the bottom, that check. Next, remainder. Not equal to 0. In this case we also have that. Right. So if this is the case, then when we have the quotient as a slant asymptote, so we say y equal to 1x minus 1 is the slant asymptote. Right, 2x squared minus 5x plus 3. Once again we find the slant asymptote, so we check the degree. Is degree on top 1 more than the bottom. And the degree on top is 2, degree on bottom is 1. By the way, I choose the denominator to be just binomial, so it's easy to divide them. If it is like this, we have to use the long division. Right. So once again, divide by x minus 1. That means we're going to put 1 there at the corner. And there's 2, negative 5, and 3. Drop the 2. 1 times 2 is 2. And 1 times negative 3. And that gives us 0. Well, in this case, remainder equal to 0. What is that? Which, I mean, the remainder not equal to 0, which we don't have. So in this case, even though we have the quotient, that is not a slant asymptote, so we say because the remainder not equal to is equal to 0, so we say so there is no slant asymptote. So what is the graph of that actually look like? So when we divide them, we just have x minus 1. I mean, so we say when we divide them, it is just equal to 2x minus 3, right? So the graph of that should be similar to 2x minus 3 though. Of course you see, it's just a straight line, that is 2x minus 3. The difference here is that when x equal to 1, the function is undefined. So it's not a line, but there's a hole at x equal to 1. So if we're going to sketch the graph, this is just as 2x minus 3 except when x equal to 1, there's a hole in it, because it's still undefined when the bottom equal to 0. Right. So slant asymptote, degree on top is 1 more than the bottom, but remainder is not equal to 0. Otherwise, we just have a hole on whatever it is simplified to. It is simplified to a line, and so a line with a hole. Right. For the function x squared minus 1 over x minus 2, we'll try to sketch the graph by finding the intercept, the asymptotes, and if it's not enough, we plot a few more points. Right, intercept. X-intercept is where we let y equal to 0. So we have x squared minus 1 over x minus 2 equal to 0. When we let the fraction equal to 0, that means the top equal to 0. And here we have x equal to plus or minus 1. Right, plus 1 on both sides, take the square root. So we have the intercept x equal to 1, y equal to 0, and x equal to negative 1, y equal to 0. Right. For y-intercept, we're going to let x at x equal to 0. Also for y. So that is negative 1 over negative 2, or it's 1/2. So x equal to 0, y equal to 1/2. Also, on this one, the domain, the denominator not equal to 0, x not equal to 2. Right, just keep that in mind. Right, so we find the intercepts. Now find the asymptotes. So vertical asymptote, we need the bottom equal to 0. And the top is not. So bottom equal to 0, x minus 2 equal to 0. Plus 2 on both sides, so x equal to 2. And when x equal to 2, the top equal to 2 squared minus 1, not equal to 0, so x equal to 2. So that is not equal to 0, which is good. So x equal to 2 is the vertical asymptote. Right. Next, we find the horizontal asymptote. Degree on top is, we have x squared minus 1 over x minus 2. Degree on top is 2. Degree on bottom is 1. So degree on top is 1 more than the bottom, so it's no horizontal asymptote. Right, bigger on the top, there's none. Right, now we find the slant asymptote. We need to check two things. Is degree on top is 1 more than the bottom. Degree on top is 2, degree on bottom is 1. Yes, so that's check. If that is the case, just go ahead and divide them. This time we divide by x minus 2, so we're going to put 2 in that corner. X squared minus 1, notice that we have 1x squared, 0x, and there's negative 1. Put 0 in because there's no x there. Right, drop down to 1, 2 times 1 is 2, 2 times 2 is 4, that gives us 3. So we have the second criteria, the remainder not equal to 0, and that certainly is the case. So in that case we have x equal to 1, the quotient. So y equal to 1x plus 2 is the slant asymptote. Right, so we have the vertical asymptote, the slant asymptote. When there's slant asymptote, it cannot be the horizontal asymptote, right? Because when we have the slant asymptote, degree on top is 1 more than the bottom, so it's already bigger than degree at the bottom. So we cannot have horizontal asymptote and slant asymptote at the same time. Right, now just put all the information we know on the graph. So the intercept, x equal to 1, y equal to 0, x equal to negative 1, y equal to 0. So we have those two. X equal to 0, y equal to 1/2. We just have those. And the vertical asymptote, x equal to 2. Right, next. X plus 2. So we have x is the y equal to x is the diagonal line, plus 2 unit. So it's going to be the diagonal line. So we have the slant asymptote, y equal to x plus 2. Right, now we have 3 points at the bottom. Now the asymptote is where the function approaching to, so it should look like this, because from this point the function approaching to the asymptote. That's what we have. Right, so here we have enough point to determine that. Now when x bigger than 2, what happened? So in that case we might have to plot a few additional points. Right, I'm just going to put 3 in and see what happened. Just plot bigger than, because here we have every values from negative infinity to 2. Now we just need something bigger than 2, like 3 and 4, see what happened. When x equal to 3, put in the function. I'm just going to put a function in the calculator. And look at the graph. We don't look at the graph later now. Look at the calculator, the values. When x equal to 3, y equal to 8. And when x equal to 4, y equal to 15 over 2, which is 7.5. When x equal to 5, y equal to 8. And equal to 6, that's 35 over 4, so a little more than 8. But I think those will be enough. So we have the point. When x equal to 3 is equal to 8. X equal to 5, it is also 8. And when x equal to 4, it is 7.5. So once again, we have those points, and the function we're approaching to the asymptotes. So it will be like this. So the asymptote will help us to get the frame of the graph. It is not part of the graph, so we know the asymptote is where the function approaching to, and if we need to plot a few more points just to get where the graph is. But other than that, that is the graph for that function. And with that, we finish section 3.5. Thank you for watching, and see you in another video in course algebra.